Alright, just my keyboard a little bit. It's gonna be a little bit crooked, I think, in frame, but it's the best I can do. I'm not sure how it's crooked when the webcam is straight, but that's gonna be how it is. So the goal for today, to do a general binary search session, keep the streak alive, and then after the binary search session, I'm gonna just go to LeetCode. That's why I changed the title from specifically binary search. I'm gonna go to LeetCode and just do as many kind of Google tagged questions as I can without burning out my brain. So I think that should be a fairly good way to start today. Just gonna wait a minute or two, see if anybody else wants to join. Okay. Actually, I think I'm just gonna honestly go ahead and get started. I'm a little late on my schedule as is, but that's what happens when you wake up 2 hours late. Alright, palindromic integer. Given a non-negative integer palindrome, return whether it is a palindrome. Can you solve it without using strings? Well, obviously the string solution is very trivial here. But I know, so I guess let's try and do it without strings. Let me change this light pattern to a better one here for this. There we go. So, a couple things to note about the properties of integers and division. Because we're in base 10, doing a mod 10 always gives us the last integer. That's one property that I know we can use here for sure. What other properties can we use? I'll go ahead and maybe zoom in the camera a little bit more. There you go. So, we can do that. Now, how do we access what the first integer is? I guess I'll just solve it using strings. Okay. String s equals num. Okay, there you go, plus num. And now from here it's fairly simple. We just do 0 I is less than num dot length, or s dot length over 2. We add I, and then check if s dot char at I is not equal to s dot char at s dot char at s dot length minus 1 minus I. There we go, and down here return true. And that should be easy to solve. If I actually add the correct amount of closing parentheses. Sweet. There you go. Very slow because we use the string, but that's just going to be how we do it for now. Next question. Merge two sorted lists. This one is an easy one, but I think it's very good practice for two-pointer. Int a pointer equals 0. Int b pointer equals 0. Then we're going to make a new int array, which is going to be equal to the length of the previous two. Because one way you could do it is to do it in n-log-n, where you just kind of add all of A, add all of B, and then sort the whole list. But that's not the way we're going to tackle it. So let's do while a pointer less than a dot length, and b pointer less than b dot length. There you go. From here, let's do that. And wait a minute, is it just because my camera's crooked? Which way makes this better? No way makes it better. Cool. Let's leave it like that then. Okay. If a at a pointer greater than b at b pointer, Let's do less than, because we want to, there you go. We're gonna do result. Let's keep an R pointer. Result at R pointer is equal to A at A pointer. And then we need to increment A pointer. The other thing that we can have happen is that B is bigger, so or B is smaller rather. We're gonna take B and there you go, and increment B pointer. And then here we're gonna increment R pointer, and this will allow us to add in everything while potentially until one runs out. So once one runs out and becomes equal to these, we can do a check as follows. If A is less than A pointer, if rather A pointer is less than A dot length, add the rest of A. While A pointer, actually we don't even need this conditional here. Say while A pointer less than A dot length, okay, while A pointer is less than A dot length, we're gonna do the same thing here and increment R pointer. Okay, and then we're gonna do the same thing for B. Alright. Cool. Return result. And that should take care of it. Not a statement. I think if we enclose this into it like that. Wait, what? Oh, new int. Forgot to declare it as a new array. Great, okay. So, change the lighting on accident again. There you go. So in order traversal, given a binary tree, return an in order traversal of a list. So in order is left, right, middle. So an in order traversal, I think we can use a queue. So let's do this, right? We're gonna make a queue of tree, queue equals new linked list. And what we're gonna do is add our root node. So first of all, if root equals null, return null, like that. Then what we're gonna say is we're gonna add our root to the queue. Make also a array list to store our values that we traverse. Just like that. Okay. While not queue.isEmpty, we're going to do tree cur equals queue.pull, add to traversed, traverse.add cur.val, And then what we need to do is say if cur.left does not equal null, q.add cur.left. Because we don't want nulls in the queue. Right, let's print out our traversal here. Actually, let's just do this. I hate this overhead of having to convert what's it called? A list to an array in Java. It's very, very annoying that they're not kind of easily interchangeable. There we go, and then we're just gonna do and we're gonna return result. This should allow us to do the in-order traversal iteratively. 180, 59. Strange. Am I mistaking what an in-order traversal is supposed to look like here? Here, let me quickly look up the definition of an in-order traversal. Because from my understanding, right, an in-order traversal goes left, right. Yeah, okay. Pre-order, post-order. Where is in order? So in order is left, root, and then right. Huh, interesting. So I guess maybe I was sort of mistaking what an in-order traversal implies. So how can we do... I guess one way I can see maybe fixing the issue that we're having here is making a double-ended queue. And then from that double-ended queue, if we add the right to the back, and then if okay, let's do it this way, right? Let's do a recursive one. So we're gonna need to keep result, we're gonna need to keep that, comment out this. We are going to comment out this, make this list a global scope thing. Then, having made that global scope, what we're gonna do is make a traverse method from root and call that method down here. That's called traversal. Okay, public void traversal tree root. Okay, so in order is left, right, and center. So what we're gonna do is say traversal okay, this conditional should allow us to check, make sure that we don't get a null pointer exception. root.left traverse.add.val, and we're going to traverse right. There we go. There we go. And that's, what's the question? The question is to do an in-order traversal, which itself isn't hard, but the main sort of difficult part of this comes in trying to do it iteratively. I guess I'll just root null return equals new int size 0. You never know what you handle with these like null cases. Null tree. Never heard of a null tree. Hold on, let me look that up. Null tree, a tree without any node. Yeah, I think that's what I was considering here. Except I was returning a null instead of a returning an empty array, which they expected. It's difficult to tell until you really run it. Alright, let's see what the last question here is. Pairwise linked list swap. Ah. This one is not fun. Given a singularly linked list, swap each pair of nodes and return the head. This one is tough merely because it's a linked list, and figuring out how to arrange these, I think they're called references in Java, they're not actually pointers. And I finally understood the difference between references and pointers after last quarter. Okay. So how can we actually go about doing this is the question. I mean, obviously it's gotta be something along the lines of so on an even one we swap the last one, on an odd one we keep kind of that last one in. So we're gonna have to start from our current one. We need cur.next, obviously. Cur.next.next. Because that's the one that we want this one to then point to. So let's what if we did something along those like temp equals cur.next.next. So temp is going to be cur.next.next. Then cur.next.next is equal to null. We sever this reference. Then cur.next equals cur. Cur then we sever this reference, and we point this back to here, and then cur.next next equals cur. So this one's next one is going to be this one. And then from here, cur.next equals temp. So what we're saying is, okay, grab a reference to this node, sever this reference, point this node back to this node, point that node to that node, and then we can do cur equals cur.next. And I think that should take care of it. I'm not sure because working with references is not my strong suit, especially in linked lists. But let's give it a shot. So while not cur equals null, cur does not equal null. That's what we're gonna do. Gonna say hope this doesn't give us a null pointer exception. It shouldn't in this case, but in odd cases we're gonna need to add error checking. Node temp equals cur.next.next equals null. I'm gonna write out this step right here. I know it's redundant, but it helps me read it better. Equals temp cur equals cur.next. We also need to keep track of the head node. Equals node. Ooh. Ooh, this is a bit of an issue. Because how once we swap that node around, we also need to update what the head points to. I guess we could just, for the time being, say head equals node dot next. Because we keep the reference to it. Head. Thought I put the semicolon there. Oh, right. Node equals cur. Or cur equals node. Just for the time being. 1, 0, 3, and 4. Okay, so we're getting somewhere. We did swap the first pair of nodes. Let's do this, right? System.out.println cur is equal to, and let's print out cur.val. Because we swapped these two, and cur should be pointing to 3 at the end of it. Yeah, cur's pointing to 3. Okay, so .next is null. It's because we're grabbing a null node from out here. And 4 is getting lost. And you also need a previous node, huh? There's a new linked list node. So, anytime we update prev.next equals cur. So let's think about it this way, right? We have our previous, it's a new node. Okay, man, this is where we kind of get to the more difficult part. So we're saying, we're grabbing this node, then we are severing this connection, connecting this one here, and previous just needs to equal current. But how do we reconnect this? Because here, previous is equal to current, which is going to be equal to 0. So we here say that, sever this connection so the node doesn't exist. Cur.next is equal to cur. This question breaks my head every time. Really not sure, honestly, where to go from here. Because what's happening is we're losing the 4. Okay, let's follow this along. 1, 0, that's the output. 0, 1, 2, 3, 0, 1, 3, 4. So after the first stage, we end up with, it's so hard to follow. So temp is equal to this. Here, let's, t is equal to that. Cur.next equals null, so there's no connection here. And then do we need a previous node? I think we might still need the previous node. Because we somehow need to reattach. head.next here. It's gonna have to equal so cur.next equals that, so equals cur.next. Crap, that just gets us to a 0. Still no. Oh my goodness, okay. What about just setting it to cur? Plot points 0 to 3. Try that. That's just a null pointer. Okay. Because we need this previous at the end of stage to be pointing to... it's because cur is null. Okay, so previous is going to be equal so point this to that. I think what needs to happen is this assignment assignment needs to happen right here. That's just a 4. I mean, we found the 4, but now we have nothing but the 4. Okay. What I'm going to do, I'm going to pull up another tab here. I'm going to grab the answer and try and follow along and figure out how this one worked, because I think it's going to be a better use of my time to grab a solution, look through it, and then continue on LeetCode rather than... Okay, let's see what they've got here. So that's my solution. Doesn't really work. Let's see what this person did. Okay. So if node is null or next null, if it's one node, we just return the node. Head is node.next. Next is head.next. It's recur. Wow. So let's see. We don't need a solution class. We also didn't need another one of these. Also don't need this one. Sweet, and then... So how does this one work? Head dot... Okay, so... Head is node.next here. So pass in node, let's say we pass in 0. Head is 1, and then next is 3. Head.next is 0. Head.next. This is weird. I'm not sure. Okay. So head is 1, this is 3. Head.next. Yes, exclamation point room, yeah. Sadly though, I'm not gonna be kind of continuing in this room. I'm gonna hop over to LeetCode in a bit here and just start solving Google tagged questions, because my interview's tomorrow and I need to be prepared. In binary search, even though it's a nice general practice set, it's a lot more difficult to do sort of very tailored questions towards Google. Okay. It's my final for Google, so it's 5 back-to-backs, I think 45 minutes each. Okay, time to hop over to LeetCode. Let me just open it up here and try. I'm not a big fan of the LeetCode editor, honestly, but it is what it is. Okay, let's pop that over. Cool. First time I'm on this site on Twitch. Okay. We're gonna do, let's see, Google 1096 questions. Jeez. All right, time to solve all 1096 Google tagged questions. If the site would ever load, that'd be great. Please. There we go. Okay, so I want it sorted by frequency. Ah, okay. So looks like, at least for the past 6 months, according to LeetCode, Google's questions are not easy. Not easy whatsoever. But I mean, let's go ahead and tackle a couple of them. Find leaves of a binary tree. Let's see what we got. So collect all the leaf nodes, remove the leaf nodes, repeat until the tree is empty. Collect the tree's nodes as if you were doing this. Wait, what? I kind of like binary search more, I'm not gonna lie. So 3, 4, 5, 2, 1 are also considered since per each level does not matter the order in which the elements are returned. List of integer. Interesting, okay. So I guess the way to do this then is okay, first of all, let's create a list integer result equals new list of integers. I think I can actually change the color scheme here. I want Eclipse. There we go. So, first thing that we need to do is we need to do this until the tree is empty, right? So, we can do this inside of a while loop. While not root does not equal null. Each time the root still does not equal null, we need to perform a set of operations to gather all of the leaf nodes from it. So what we're going to do is say result.add. So gather. We're going to pass in result. And down here, we're going to make another method called gather. Public, and it's going to return a list of integer. Gather, and we're going to pass into it a tree node. There we go. Okay, so this tree node, a leaf node is defined as a node that has no children, right? So I'm trying to think of how to do this iteratively, right? Because we need to do I think can we do this in one step? I remember because for the first question I was doing a level order instead of an in order traversal. That's why it wasn't working. So, I think what we can do, right, is to do a level order traversal. And level order traversal, keep track of... No, we can't do a level order because then we can't keep track of the parent. Can we? Because we need to, basically at each step, check, hey, it's either am I a leaf node or are my children leaf nodes? I think it's easier to check for children. Check, is my left child a leaf? If yes, add left to list, trim left. Is my right? If not, add it to queue. And I think that should allow us to, at every level, trim off the respective leaf nodes. Yeah, I think that should be good. So let's do this, right? Let's do queue. This new linked list. Got to specify that it's a queue of tree nodes. Now what we're gonna do is do queue.addRoot. Cool. Now comes the fun part, where we set up our while loop. There we go. So while our queue is not empty, what we're going to go ahead and do is to say check if queue.left does not equal null, then we can do one of two things. If queue.left, we're going to do pull from the queue actually. Cur.left. Left does not equal null, or cur.left.right does not equal null. Basically saying, hey, we know that our the left child of this node is not a null, meaning it's present. Then, if it has no children of its own, it's a leaf node and we need to trim it. So in this case, if it's not a leaf node, then we do queue.add cur.left. And then, otherwise, if both of those are else, I didn't actually make my list to store these things in. List, integer, leaves, new array list. Cool, gonna do that. And then we're gonna say leaves.add cur.val, and then we're gonna, not cur.val, let's do this, right? It should take 2 steps. For, let's do int index equals 0, while index less than 2. Let's do that. 3, 4, 5, 2, good, good, okay. Okay, let's do 3. What does 3 give us? That works. But, okay, let's do 4. What does 4 give us? A TLE, doesn't it? Because the root node is never cleared. It works, the root node was just never cleared. So this should give us interesting. Okay. Let's do while root does not equal null. Weird. Okay, so it's just a little issue with getting rid of this root node. But why? I mean, the algorithm itself works. It's just a matter of So yeah, that should take care of it. I'm not sure why it's not. What if we tried root dot null? See what that gives us. Cool, and that just drops the root node. Okay, so what we're going to do is just say list we're going to do result last.add root.val, and then afterwards what we're going to do is say result.add last return result. Cool. Not the fastest by any means, but it works. I think, I'm not sure why we're having the issue here of root not being updated. But it's not. Because I guess one thing that we could maybe try and do to make this faster, instead of doing this, we can say while root.val does not equal -1, for example. That should allow us to, I think, get rid of this. And here, root.val equals -1. Should allow us to get rid of that overhead. Yep, and then it should be a bit faster. Yeah, I mean, not by much, but overall, pretty good question. I'm pretty happy with it, honestly. Let's see what else we have in terms of Google questions here. Okay. Problems. There's Google by frequency. That was a fairly challenging one, though. I'm glad that I solved it. It gave me more practice working with trees. I'm going to step out for a bit of a break here and then come back, and I think we'll probably end up doing one more problem, one of the more common ones. Okay, let's see which other question we can tackle here. Maximum number of points with cost, that's DP, I'm not doing that. Guess the word. Snapshot array. What is snapshot array? Initialize an array-like data structure with a given length. Initially, each element equals 0. Sets an element at the given index to be equal to val. Take a snapshot of the array and return snap ID. The total number of times we called snap minus 1. Returns the value at the given index at the time we took the snapshot with the given array. I guess what we could maybe do, it wouldn't be... Okay, so most 500,000 calls. So, okay, here's what we're going to do. We're going to first of all, so this initializes an array-like data structure with the given length initially equal to it. We're going to use a map of lists. So we're going to use a hash map of list of integers. So what we're going to do is initially set everything equal to 0, right? And then basically treat every time we get a snapshot, we're going to iterate through it and add the item to the map of lists. So we're going to initialize it with a given length, right? So hash map wait, hold on, equals new hash map of list of integer. Then for int I equals 0, I is less than length I plus plus. We're going to do map.put at I a new array list of integer. Cool. And we're going to do map.get I.add a 0. Just going to do that. Cool. Because it needs to start at a 0, and that should allow us to initialize this. Return 0, sure. Let's do this right here, right? println map.toString. I want to see the monstrosity that is going to be this thing. Keep forgetting that I need my closing caret. Oh, right. Integer for index and like that. Where does it give us the length? Okay, 3. 1, 2, 3. That's cool. Yeah, that's that. Perfect. Okay, now what we're gonna do is, I think, first of all, implement snap. Okay, we're gonna first of all keep a counter int snaps equals 0. So 0 is going to be taking a snapshot of the initial one. So what we need to do whenever we snap is to say add the current state of the 0 index to each list. So for I equals 0, I is less than map.size I++, we know that we can access each of these indices because we made them at the beginning. So we're going to do map.get I dot add map.get I dot get 0. So what this should do is add the very first element that we're current, like a live array, to the end as a snapshot. And then return so we're going to do snaps plus plus. We're going to do return snaps minus minus. There we go. So the thing is, now whenever we access this, we're going to need to access at a +1 index. So for get, we need to do map.get at index. Map.get at index dot get at snap id +1. Snaps, not snap. Wrong answer, that's okay, because that's okay. Now we're gonna need to update set. Hey, good to see you, Pizza City. How you holding up? Okay. We're going to do set index val. So we're going to do map.get at index dot, I think, here, let me look, Java list. I think it's set. And it should be set, yeah. So we're going to set index 0 to val. Perfect. Should be that. He's also going to practice some LeetCode today. Yeah, I've been doing this for maybe, what, like hour now. Hey, there we go, sweet. So if no edge cases. No, time limit, it's too slow. Not this question for an hour, no. I did a full set of binary search questions, and then, binary search, then I did like a more common Google one, and then, yeah, it's the snapshot array. How can I optimize this, though? That's my question. I'm not really sure, sort of, what this is supposed to be. Because the map... I think the slowest thing here is taking the snapshot. Because accessing the snapshot is O of 1. Updating a value is O of 1. It's just a snap. Ah, their instruction set is very painful. So I think if there is going to be any optimization to do, it's going to be to the snap method. What's a faster way? Says the question, array-like data structure. Yep, that's kind of what I'm doing. My array-like data structure is using a map. Hey, good to see you, man. Good to see you. Because, yeah, my array-like data structure is a map that's using an index and then storing a list. Yep. Tomorrow is my final. Tomorrow determines whether I land a job at Google or not. Do I feel prepared? I have no idea. No idea. Yeah, I'm quite literally not sure how to optimize this. It would have to change, my interview is, I think I start at 10 a.m. and end at 3:30. Yeah, thanks, man, I appreciate it. Here's hoping, here's hoping. It would be really nice to say that I managed to land a job at Google. Though I'm not quite sure if I'd even, like, if I landed it. I have my Microsoft interview coming up after, which I'm kind of looking forward to more, if I'm being honest. So, it'd be kind of a flex to say I landed Google and rejected them. But I gotta land Google first to do that, you know? So, optimizing Snap, right? Okay, in that test case that exceeded the time limit. Snapshot array of, how much is 1, 2, 10,000. Is it for an entry level? Yeah, it's new grad entry level. But even for that, like, Google standards are pretty high. Considering every single developer applies to Google. Goodness, I don't know how to optimize this. Yeah, that's why I'm kind of banking on Microsoft, because Microsoft has a lot lower standards. Yeah, I don't know how to optimize this, man. I don't know how to optimize this. But I do gotta finish up because I ran overtime today already. I'm gonna leave this question as is. It's a solution. If they ask about potential optimizations, do they have a solution for this? No solution for this question. Okay, look at the discussion. O of 1 snap. That's what I want to see. I want to see an O of 1 snap. With tree map. Tree map, integer. So he has a snapshot ID. Better announce it. Announce it if you get it. Unlike last time, you disappeared for a month. Yeah, it was like the holiday season, and I had a lot to do, so kind of vanished. I will definitely announce it. I'm not sure how long it's gonna take him to respond because I know Google has. Are you going on site or phone? I think it's all phone, which makes it a lot easier. But yeah, Google. I think their turnaround time is like weeks before you really know what you. I'm pretty sure I'll know if I failed, though, right away. If I'm unsure, I won't say anything about it. Okay, so he has a tree map array. Snapshot ID is 0. New tree map.length. Makes the tree map. Map. Oh, I see what they did. Oh, virtual onsite, an earlier one. It's the virtual onsite. It's the final. Like I'm done after this. It's my last one. So, what exactly is a tree map? I have a vague idea. I guess an array of maps where you store it is technically faster than a map of lists. So, okay. Let's see. Tree map. What's a tree map? It is a red-black tree-based navigatable implementation sorted according to the natural ordering of its keys. So, I guess if I were to make an array of maps, I could then have constant O of 1. Oh, that makes sense, yeah. No, this makes perfect sense now. Because in my solution, it is O of 1 access, but it's not O of 1 to add. I think adding to add to end of list runtime. Let's see. Man, I guess I'm not sure why that. Oh, I can see why my snap is slow because of this for loop. His implementation of the snap method allows him to just move the index up by 1 for everything and then start modifying that array. And every time he needs to access the snap method, if we go back to Java solution with tree map, every time the get is done, makes a new map and looks for that target. If it's not null, if it's null, return 0, otherwise we get it. Pretty much checking, hey, is that target present in the map? So rather than every time you take a snapshot having to do a for loop, you just up the ID and then accessing, you just target that ID. Pretty clever. Pretty clever. Alright, I'm gonna go for now. I might be back later today, might not be. I might just do some individual practice on topics that I'm feeling a bit rusty on. Tomorrow, no stream, because of Google interview. And then, hopefully, hopefully get a job. Whew. Okay, that'll be it for today. Thanks everyone for stopping by. Hopefully, make sure you get 8 hours of sleep. I'm gonna do my best to get those 8 hours. I've always found that helps more than anything. To wake up maybe an hour or two before, have a clear mind, kind of have my coffee. I mean, I always have my coffee with me, but it's the best debugger, yeah. And I'm just gonna hope and bank on getting no dynamic programming questions, because if I get one, I fail the interview, and that's that. So, all right, take care, everyone, and thanks for stopping by.